This is an example of confidence intervals for one proportion. I have the formula laid out here. It's my center p hat, that's my best point estimate, plus or minus this entire thing that I'm adding and subtracting is called the margin of error. I'll abbreviate that as the MOE. This critical value z star, this tells me the number of standard deviations out on this normal curve that I need to go to get a certain percentage. And this is my estimate for what the standard deviation should be. It's my standard error. So to use this formula, I have to figure out my sample success rate if it doesn't give it to me, my sample failure rate, the number of samples, and I also need my critical value. I'm going to give you a critical value for a couple different confidence levels here. So if we wanted to be 90% confident, I'm going to use a critical value of 1.645. These are really common values, they show up a lot. If I want to be 95% confident, I need to go 1.96 standard deviations out. And if I want to be 99% confident, my critical value for that is 2.576. I'm going to find my sample success rate by taking the number of successes divided by the number of trials. In this problem, I had 45 successes. This was about orange tabbies and cats in the Portland area. I sampled 120 cats, and out of the 120 cats, 45 were tabbies. When I type that 45 out of 120 into a calculator, this gives me a 37.5% success rate. So if I was asked what percentage of all cats are orange tabbies, I currently have an estimate. I think it's about 37.5% or so, give or take something. This entire margin of error, this is how much wiggle room I have in this estimate. So if I have a 37.5% success rate, my failure rate is 1 minus is 62.5%. P hat and Q hat are complements, they're opposites of each other. And I had 120 samples. So I wanted to be 95% confident. I'm using a critical value of 1.96. My square root is going to be my success rate. That's that 0.375 number. My failure rate, that's the 0.625 number, divided by the total number of samples. And I'm going to break this up into smaller pieces as I go, just so I can practice the terminology as I type things in. I'm going to type in this square root. This is going to give me my standard error, and I get a standard error of something like 0.044 or so. I'm going to type in 0.044 times that 1.96. So I estimate that 37.5% of cats are orange tabbies, give or take a margin of error of 8.62% or so. If I type this in once with the minus, I'll get my low value. If I type this in again with the plus, I'll get a high value. I'm going to go ahead and do that. 0.375 minus 0.0862. I get a low value of 0.2888 or so, so I'm just going to call that 289. And on the high end, I'm getting something like 0.461 or so. You're welcome to use more digits as you're working through these problems. I'm just using 3 decimals here as I'm kind of going through stuff. Whenever I write down my confidence interval, I have a sentence that goes along with it. That sentence frame will look something like the following: I am or we are blank percent confident that the interval of blank to blank contains the true or the population percent of whatever we're working with. So in this example, I was 95% confident. I used that 1.96 critical value, and I ended up with an interval of 28.9% to 46.1%. So I'm 95% confident that the interval of 28.9 to 46.1% contains the true proportion of orange tabbies in the Portland metro area. So again, the formula that I'm using to come up with this stuff is p hat plus or minus z star square root p hat q hat over n.